So I'm incredibly excited to be developing and applying new mining exploration technology. Again, that's been my passion since I was 16 years old when I worked on my first mining exploration job in central BC with Malcolm Hurd with Chapman Griswold. And I've never quite, fortunately, never recovered from the experience. Still having fun doing that. In the last 6 years, we've been, PhotoSat's mostly been surveying mine sites, operating mine sites around the world. And in the last couple of years, we've started to do a little bit of exploration again. There's been funding and new technology. So that's what I want to tell you about today.
Sorry, Gerry, just before you start,
yeah?
I just want to make sure your microphone is on.
Does that help? Yes. Okay, thank you very much. All right, good. Okay, and then I'm supposed to stay away from that, otherwise we'll get feedback. Okay, so does that work? All right, so I promised not to do too many digressions here today. So what I'm addressing is what are the new tools and how are they developed? I want to talk about the technology, the team, the Cooperite, Nevada, NASA and USGS test site that we all use, and then the Juanicipio epithermal silver deposit, what we've seen there, Ixtaca epithermal gold, Red Mountain, I'm not sure what to call that one. Every geologist I ask says, well, I'm not sure quite what it is, but there's gold there. And then we'll talk about the Aster and compare the Worldview 3 to the Aster. So that's where I'm going to try to stay, although there's lots of stories to tell. So Andrew will probably help to keep me on track here. Okay, so the new technology that's making this possible. First, there's this incredible Worldview 3 satellite. There are probably 30 satellites up there that we use for one application or the other. This is our favorite bird in the world. We use this for stereo satellite elevation surveying and mine sites around the world, and now for the alteration mapping. And the three folks from Digital Globe here, Christina, Chris, and John are here on the front row, and this is their satellite. And it's just an amazing bird. And then the other piece of technology that makes this possible, these kind of results, are these graphics processing units. It's a GPU with 4,300 cores. This has got processing capacity that I know 20 years ago would have cost us millions or tens of millions of dollars. and that's when actually most of the existing alteration processing software was written and was sort of 20 to 30 years ago. Most of the algorithms, we can do things now we just could not dream of doing then with these numerical processors. So we have to thank the video gamers, but not that much. Okay, then the Worldview 3 satellite. Gabrielle and I were there for the launch in Vandenberg Air Force Base on August of 2014, and we had that view of it. It was really spectacular, and I've been in love with this satellite ever since. Okay, so then the other piece another piece is the software development. This is our software development team. This is the team that developed the highest accuracy stereo satellite elevation surveying in the world. We used to call it mapping. When we got our accuracies better than 15 centimeters in elevation, all of a sudden, all of our customers were mining engineers and civil engineers, and we became a surveying company. And engineers think that maps and mapping ought to be free. We know it's not, they're not, but they do. And so surveying, they're used to, they know that that's valuable and expensive. And so we became a surveying company, and they're surveying products. No more DEMs or DSMs, any of that GIS jargon, it's survey grids. Now, anyway, so this is the team that developed that technology and is now, for the last 18 months, has been working on the multispectral satellite image processing. And the software development tools are amazing. I mean, 10 years ago, a small company like ours couldn't have dreamed of doing this kind of development. with tools, with intuitive, interactive, or processing tools for the processors. And now with these tools, you can build things. I mean, it's like when I was a geophysicist in the 70s, we all wrote our own code. Then it was all commercial software. And now we can write our own code. Well, I can't write the code anymore, but people who were my age when I was in the 70s can write the code again. It's amazing. Okay, so there's our production team that actually does the processing. Those are all physics grads. They know what cross-correlation is and spectral matching. And know the fundamental principles of all the physics. They know what should happen. And so they do all of our processing. And then we have a geologist who checks everything for being geologically reasonable at the end of the process. And then there's our customer service team. Those are the people that you all deal with who help you decide what's the most cost-effective mapping or surveying process for your project, and then guide the project through and give you feedback on how it's going. And I think their fundamental value, one principle is that want to be absolutely sure that we create value in every one of your projects. If we don't think we're going to create value, we frankly won't do it for you. Which kind of disappoints some folks in triple canopy jungle in Ecuador who want to do alteration mapping, and we say, no, we won't do that. We can't see any rocks. Okay. All right. So then, well, I should check how I'm doing for time. Andrea, are you sort of watching time here? Okay. I'm okay? All right. So, Cuprite, Nevada, this has been the test area for multispectral satellite and airborne process development, mapping development since the 70s, since the first Landsat. And it's a huge epithermal alteration zone with lots of big outcrops of all of the minerals. A spectacular place to test with. No vegetation of any sort there. And so the dilemma is that, well, the good thing is if you got something that if it doesn't work in cuprite, it won't work anywhere in the world. But just because it works in cuprite doesn't mean it'll work anywhere else in the world except cuprite, the Atacama Desert, and the Namib Desert. A little bit of vegetation and you get false positives everywhere, which is one of the real challenges. And cuprite, I mean, it's obviously the geologists named all of these topographic features. We got kaolinite hill and alunite hill, and opal hill, dickite ridge, and buddingtonite bump. The topographic features. So if you're doing your process testing, you know where you should be getting the right anomalies. And this is hydrosilica, which is opal and chalcedony to the right. Okay, and there's buddingtonite bump and the Worldview 3 spectral match for the 16 band over buddingtonite bump and with a black background. So we know we got it there. And so we can do all the testing there, and then we go everywhere else in the world and discover that we find those anomalies, but we also find another 100 that are caused by dry vegetation or some other feature that doesn't exist on this project. So cuprite. So we did our testing in cuprite, and when we were developing this technology, we were working with a couple of companies that provided us with a lot of ground mapping and a lot of their ground terraspec data. And they were very generous with sharing all of that with us. Unfortunately, they're not prepared for us to share this with you. And so we were producing some spectacular results. We said, oh, we'd like to present a paper at the RoundUp or the PDAC. They said, not on your life, not with our data. And so we went to our friends at Digital Globe and said, can you shoot a couple of projects for us so that we can talk about? Juanicipio in Zacatecas, Mexico, and Ixtaca. Juanicipio is mag silver, discovered by famous geologist Peter McGaw, and Ixtaca discovered by Morgan Poliquin, that I'm sure 2/3 of the people or 3/4 of them know here. And before we look at Juanicipio, first, okay, so that's with this Worldview 3 bird. I am going to talk about some of this spectral matching, probably a little too much, but that's the alunite on the left and the kaolinite on the right, and of course they've that one geological traverse across there would pick up either of that, so that's not real news, but we are seeing those. Okay, a little bit now about a little bit more about this bird and its spectral bands. So there's 16 spectral bands on the Worldview 3 satellite. In 2 meter pixels in the visible and the near infrared, 8 bands there, and then 7.5 meter pixels for the shortwave infrared. And if we compare that to Aster, you see that it's 16 times the horizontal resolution. It's also, these are all 11-bit. The Worldview 3 is all 11-bit, with the Aster's 8 bits, so that's 256 dynamic range compared to 4096. I've got my math right. And so it's much better data, much higher signal to noise, and really spectacular data. In terms of what the impact is of the increased spatial resolution, I'll be showing some actual examples later on, but just conceptually, if we have a small area of alteration on the Worldview 3, we'll be able to get a few pixels of it. On the Aster, it's going to be averaged. And so if it's just a small occurrence, we won't see anything on the Aster at all, which we will now detect on the Worldview 3, and I'll show some examples of that. Okay, and then thanks to the USGS and the American taxpayer, of which there are a few in the room here, there's this amazing spectral library the USGS have of thousands of hundreds of minerals, actually I think probably thousands of minerals and all kinds of other samples. And so we can take that library, the minerals from that, resample it to the Worldview 3 bands and see what we would expect to get. The sorts of problems we might be able to solve from that. And if that's just kaolinite and alunite, and if we zoom in on that a little bit, there's lots of details in the spectra that we don't get, but you can see clearly that that if you're alunite from band 4 to band 5, it'll drop and then go up to band 6 and band 7 and back down. Where if it's kaolinite, band 6 will be lower than band 5. and so there's more to it than that, but those are the key spectral characteristics that to distinguish the minerals. So then back to Juanicipio. Okay, so we have the alunite and the kaolinite we've picked by spectral matching, and then we found these small matches of buddingtonite and hydrosilica. Now we know from the Mag Silver 43101 report that they've got silica cap there, so we would expect opal or chalcedony, or at least silica cap is a lot of massive silica, but you do get little zones of chalcedony and opal, and if you got those, you're not guaranteed to be in the silica cap, but it's much more likely. And then the buddingtonite. I had to look up buddingtonite when I first was doing this. It's an ammonia feldspar. Never heard of it, but apparently it's and Peter says he has seen buddingtonite in the core at Juanicipio. Because when we sent these reports out to Peter McGaw and Morgan Pollock, I never did get any feedback from him. Morgan didn't make any comments at all, but then he almost immediately ordered 3 different projects. So we thought that was the best kind of feedback we could have. And Peter was sending customers to our booth all day yesterday. So although neither one of them actually said this is right. But those of you who know the 2 characters will not find that surprising. Okay, so anyway, so there's our hydrosilica, either chalcedony or opal, and you take the last 5 bands of the Worldview 3, you get this little shape. It looks like a serving spoon, a soup spoon. And for budding tonight, we've got a spatula. And remarkable the number of, there's probably, I think there, yes, what am I?
I'll give you a time indicator. Go ahead.
Oh,
Track time.
I've got 5 minutes left? You're joking. Good luck with that. Okay, all right. Anyway, okay. So, the number of, because when we started doing this, we looked at what had been people been doing for the last 20, 30 years, what we've been doing, and there are 20 or 30, maybe 50 spectral geologists around the world. I think one of them's in the room here, can actually look at the spectra and say, oh, that's hydrosilica, that's kaolinite, without any USGS spectra at all. But there aren't very many of those, and we couldn't do very much processing based on hiring a bunch of those people. Okay, so from Juanicipio we go to Ixtaca. There, okay, so there's their discovery hole drilled in. Jerry, you would know. 2010? Anyway, okay, yeah. Yeah, 2010, 2012, yeah. And they're in the process of your feasibility right now on this. Okay, so we've got the kaolinite with little recurrences of alunite. There's alunite in the core. I don't think anybody'd seen alunite on the surface. And then there was buddingtonite. Okay, and I was convinced, when you look at the spectra, it's got the spatula, it's buddingtonite, looks just like the USGS spectra. And I was absolutely convinced this is buddingtonite until Morgan said, actually, spectrally it could be ammonia illite. Because when we put our TerraSpec on ammonia illite and buddingtonite, we can't tell the difference, and neither can anybody else. So you're certainly not going to do this with a satellite. But if it's ammonia illite, it's a hell of a lot more significant than if it's buddingtonite. So that's exciting. Anyway, and these are small occurrences where I don't think it's ever been seen on surface there, and because the big kaolinite alteration zones. Morgan found this there was a kaolinite mine on the project. They drilled underneath that. What's it? But to find these kinds of small occurrences would simply take hundreds or thousands of hours of field mapping. And the fact that we can identify these on the Worldview 3, I don't know that you're going to find a deposit that you would never otherwise find. You might, but certainly going to take you into the right part of it sooner. You get there maybe in year 1 instead of year 3 of your program. Okay. So then, with the RoundUp coming, we thought, we need a golden triangle example. So we've done some work there, but nothing we could show publicly. So we looked at the 16-band archive, and sure enough, there were some archived 16-band Worldview 3 scenes. And so we went to our friends at Digital Globe, and they generously provided us. I think about 3 weeks ago, we got this Worldview 3 image over Red Mountain, which I don't know if anybody here wants to venture what kind of deposit that is, but I think it's the zone's been up and down, a few zones, several. Okay, so we processed it. This was just last week, and here hydrosilica, so we get some hydrosilica response over Red Mountain. Then we got something across the valley from it as well. And then on the Gerry site, we get this light bulb right over the deposit, which I don't quite understand. We've seen this now on 3 different projects. The other 2 we can't show, where we've got a very close correlation between jarosite and gold assays on surface. So, but that's, and if we compare, there's the ferric iron oxide, so that's everything. If you're flying over the helicopter, all of that will look red. Okay, so you may eventually get to to the Red Mountain deposit, but certainly when we pull just the jarosites out of those ferric iron oxides, we get a light bulb right over that deposit. Okay, so alteration deliverables. Okay, so what we're seeing so far, the hydrosilica, hydroxyls, everything with an OH, because there might just be a little bit of cerussite and a little bit of alunite, not quite enough to really kick on either of them, but there might be enough to be able to actually pull that above the background. And then the alunite, kaolinite, and the buddingtonite and or ammonia illite. Cerussite, because we can't tell the difference between illite, muscovite, and paragonite spectrally with the WorldView 3, so we call it cerussite. Mineralogists cringe every time I say cerussite. But the hydrospheric iron oxides, we're seeing guthite, jarosite, and I actually thought guthite was going to be the more significant one, but that's back from, I think, the 1970s or probably 60s and 70s. Kennecott's little credit cards all the Kennecott geologists had that had the different colors of iron oxides and which ones to look for, and the guthite for the copper guys was important. Ferric iron oxides, we're seeing hematite, and of course all the ferric iron oxides, we're seeing carbonate. And then, no, at cuprite we can distinguish chloride and epidote. Everywhere else we do that, we get a lot of false positives still. We think we'll be there in 3 or 4 months, but we haven't cracked that yet, so we're just lumping that together and calling it prophylitic. And then there's some context images. Okay, so then, well, this was really recently, actually, a couple of months ago. We said, okay, well, what can we do with this global, now we got all these new processing tools, what if we turn them onto this global Aster archive? Can we squeeze more information out of this than we can with the, than we could before? And so, and the reason you want to look at this archive when it's global, so there's data everywhere, pretty much everywhere. Bits of Ecuador have never been cloud free, but and it covers huge areas. I mean, there's a WorldView 3 photo compared to, these are actually 3 Aster photos, but they're 60 by 60. They fit together nicely, and so we looked at that, and so well, the Aster, there's their thermal band, so we can see all the silica, but we cannot distinguish the hydrosilica. The hydroxyls, everything with an OH band. Well, we've been doing that ever since the Aster was available. With our conventional processing, we were always have a lot of overlap between alunite, kaolinite, and cerussite. Now we're doing much better at separating those, and in some environments that's important. The cerussite, now guthite, whether we're not seeing the jarosite at all, or whether we just can't distinguish from guthite, we're not absolutely sure about that yet. Hematite, all the ferric iron oxides, we're getting calcite and the prophylitic. And whether with the Aster we'll ever separate chlorite and epidote, I'm not sure. I mean, other than at cuprite, of course. Okay, so we look at that that Juanicipio, the sort of thing we do with the Aster now. So we can separate the alunite, the kaolinite. There's a bunch of cerussite here, but it didn't really define any targets. Juanicipio shines like a light bulb. I think T2 has had about 30,000 meters of drilling. There actually isn't anything there but a big epithermal zone. There's no gold in it, or silver. It's silver. But, I mean, it's the sort of thing that you can do with Aster now. And And we are doing a really good job now of separating the kaolinite from the alunite. This over here to the west, the Spectra 1 is actually from a kaolinite pit, and we don't get any alunite response from it at all. So that's that's really encouraging. Okay, so comparing them spectrally, certainly the Buddingtonite and the ammonia illite and/or we won't see anything but worldview 3. The jarosite we're only seeing in worldview 3. The real big news though is the resolution and what that means. The thing is, in order to identify any of these minerals, you need a few outcrops or a few pixels that are mostly that mineral. If you've got if you have kaolinite and alunite and some hydrosilica all in the same pixel, you can unwrap it maybe. But if you never get one of those pixels that you're absolutely sure of, it's really tough to do. Where with the worldview 3, you're much more likely to know what it is, have much more confidence what you're doing. So here, and here's from the Juanicipio project. So there's the aster alunite on the right, and the worldview 3 alunite on the left. And you can see now some of these bigger zones, and there's probably fewer Is that you?
No, that was your calendar.
She set me up. Okay, and then you can see down in the center, we're simply not getting anything on the aster. And the same thing here. Here's a small, very definite alunite anomaly on the worldview 3. Same area. We pushed that as hard as we could. There's no way we can identify any alunite there on the aster. So we will pick up. Now in vegetated terrains, that's going to be really important because you only get the odd outcrop that you're actually able to see on the satellite data. Okay, and if it's a really small outcrop and you've got a fir tree in it or a cactus, depending on where you're working, it's going to be tough to get that nailed down. But with the worldview 3, you can do a much, much better job. Okay, so in summary, we can get small alder outcrop reliably, like the Buddingtonite at the silica cap. We can see jarosite and guthite, and jarosite could be more important than I thought it was. We get, of course, the Buddingtonite and/or ammonia illite, which could be really important. We get better discrimination of the mica and clay minerals, and we get 16 times the resolution we had with aster. And the aster improvements, we're getting better discrimination between the clay and micas, and we're getting the hydrous iron oxides. Okay, so and the Juanicipio and Ixtaca reports are on the website. You'll be excited to know that the Red Mountain report is in preparation.